Hello everyone again, and thank you for joining me. This is another episode of Darko's Game Dev Cookbook, and it's a pleasure to have you here again. The first thing I want to say is thank you for all the positive reactions I got for the first tutorial. It means a lot. Also, if you haven't subscribed so far and you like this and you want to see more, please do subscribe. It's very much appreciated. Today's tutorial is going to be covering basic directional light, and that's the first step towards getting to real illumination in our ray tracer. The direction we're going to be taking with next tutorials is going to be even more interesting than we had with previous tutorials, since our scene is going to become more alive and it's going to get more interesting as we go. I hope you watched the first tutorial so you can follow through. If not, that's okay. Feel free to use the shader or the code of the shader. I'm gonna leave the link below in the description. If you have any comments or any questions for anything I say during this tutorial, feel free to comment and I'll get back to you. And yeah, enjoy. So let's start with directional light for real. Directional light is a type of light where all the rays of that light source are perpendicular to each other. In the real world, you usually don't have that light, pretty much. Although the light we get from the sun, we can consider that light to be a directional light, just because of the whole scale of the universe and the size, and the distance from the sun and the size of the sun compared to the Earth's size. Those rays are basically perpendicular, and whenever we do any sort of optics, you can, like, if you remember those graphs you drew in high school, you always have rays that are pretty much, they go straight. There is no weird behavior with them. So but basically it's a directional light you're working with mostly. There's also point light. Point light is a bit different, and we're not going to tackle that right now. If you remember the last tutorial we had, I said we're gonna do some illumination or lightning on this sphere, but it's actually gonna be it's gonna be faked. Now it looks like we're holding a flashlight and we're pointing the flashlight towards the sphere, because the brightest part of the sphere is the center of the sphere, and as it goes away and it goes in a bigger angle, we get darker color tones, as in this scenario we see on the screen. That gives you the illusion that we're looking at a sphere, or not an illusion, it's for real. But if we didn't have this shading, you would have a circle, as I said in the last tutorial. So what we're gonna be doing now, instead of us holding a flashlight and looking just straight to the sphere, and actually we're also moving up and down, because you would see differences if you just stood like this, we're gonna make a light source that's gonna have its direction. And position of that light source is not relevant whatsoever. Directional light is, you can just think about directional light as this: there is something super far from us that shoots rays that are perpendicular to each other, and that's pretty much it. Only thing that you care about is direction, and depending on direction is going to illuminate different parts of the sphere. So let's start doing that. This is the simplest form of illumination you can have, and I think you're gonna be able to grasp this quite quickly. The last time we did this, we intersected the sphere, then did some stuff with the color and so on. We're gonna change this a bit. We might refactor it as well slightly. I want us to have the color as the property of the sphere. So what I'm gonna write color over here, and then we're gonna set the sphere color inside of setup sphere. And we're gonna take the same color. I think it's quite neat to take the same color for now, just so we can do these comparisons between results of different sessions we're gonna have. So now we have the color here, and then instead of returning this color over here, we're just gonna use this one. So it looks the same. That's good. That's how it's supposed to be looking like at this point. Then we did, what is this? Okay, this is the reflection that I made the last time, which is basically it's not a reflection. It's just a number that tells us how what the angle kind of is between us and the normal of the surface normal of this sphere that makes this illumination possible. So we will not need this one anymore, so I'm just gonna kill it straight on, just kill it. And we can also kill this thing over here, and we're gonna kill it over here as well. Now it's not gonna build because we're also passing it here, so we need to kill it here. Now it's compiling, and of course as soon as we don't have this reflection thing happening, or however I called it, there is no shading, we have a circle. It is a sphere in theory, but we are still transforming it onto these screens, so it looks like a circle. And now let's introduce a light. So a light is, in this case, it can be an object, as we made the sphere and camera. It can just be its own object. So we're gonna do this. I'm gonna call it, let's call it light for now. Let's not complicate the names. Lighting. And what did we say? Do you remember what I said about this directional light? That's far away, perpendicular, and it has only one property that's in our interest, and that is direction. So we have direction, which is a normal vector that's normalized. So I'm gonna do this. So we have the light, but it's not in the scene yet. So let's move it to our scene, or set the direction in our scene, kind of. We're gonna say light direction is, so I'm gonna do this. Okay, so we said that the position of this light doesn't matter because it's a directional light that's super far away, and we don't care about the position of it. We care about direction only. So we need to set the direction so it illuminates a certain part of the sphere. So if we say that the direction of our light is gonna shoot upwards, that means that it's gonna illuminate the bottom part of the sphere more, and it's gonna gradually become darker on the top. If we put the direction so it's shooting in the towards the negative part of the y-axis, then it's gonna be the opposite. We're gonna illuminate the top part of it. If we let's set it so it shoots downwards, and if you remember from the last session, if you want to have a directional vector that shoots downwards, that means that you need to have a negative y coordinate in that case, so it points down. So in this case we can write 0. So we want to go negative on the y-axis. We're gonna -1, 0. Is this vector normalized? This vector is normalized because it has length 1, because obviously it has -1 and all the other coordinates are 0. But the thing I like to do with these kinds of things is this. It's not optimal, it is stealing time. It's not, you wouldn't do this if you were doing a real thing. You would do this, this whole setup would look completely different. But for this scenario I'll just put normalized, because when we start playing with different directions, that I'm pretty sure we will, we might forget to normalize this vector, and that really makes a difference. It is gonna screw up our calculations down the road if we don't normalize it. So I like to keep this normalized here, so when I change it I don't think about it anymore. It just normalizes. It's normalized all the time, pretty much. So we have the direction. It's shooting downwards. So what do we need to do now? Now the good part starts. We will not have any complicated math as we did the last time. I'm sure you were super thrilled with that part. Some of you may have been. I'm glad if you did. But in this scenario, we're just gonna do a bit of drawing, and you're gonna figure it out pretty fast. So we have this direction, and this direction needs to affect how the color of our sphere is being rendered. How do we do that? Well, obviously, it needs to have something to do with surface normal of the sphere, so the vector that goes from the center of the sphere towards the surface, and the direction of the light, because yeah, that's how these things work. So you have the light basically hitting the sphere like this, and then there's this vector that shoots up, and then the way they interact is gonna cause different coloration of the sphere. So I'm just gonna quickly draw something so it's clear what's happening. By the way, this tool, it's called Draw.io, and it's super nice. You can draw things pretty quickly. So I said directional light is just a bunch of perpendicular rays. There is no position. So in theory, if I put it like, if I put the ray like this, that doesn't mean that the sun or the light is here and it's shooting light like this, and then there are rays all around the place. It's actually, directional light is more like this. So it's just basically all existing grid of rays that are perpendicular. So I'm just gonna quickly undo that. But for the sake of this lesson, let's say we have this direction, or in this case we have this direction. So we're shooting rays downwards. Our sphere should be brighter on top. So this is the sphere center. I might zoom that in. It's easier if we have a light that has, for example, this direction. So we have this ray. It's hitting our sphere somewhere. It can be on the edge. It can be, or I mean, there's the horizon kind of. It can hit the sphere in any other point as well. So it can hit it somewhere here, which is in front of us. For this explanation purposes, we're going to keep this arrow on the horizon, just because it's easier to draw it. So we are looking at the sphere. The light is dropping on the sphere's surface, and then how do we color this pixel over here? What's the color? Well, it depends on the angle solely. In this model, that's super basic. There are a lot of different shading or lighting models. We're gonna go into those models in the next lesson. That's gonna be a super fun one. Those are my favorite things, so I enjoy doing that, and I think you'll enjoy it too. But for this one, we're just gonna do simple shading, which is diffusal. There is no specularity or reflections happening. Just the diffusal lightning. This line, this ray over here shoots this sphere, and then we have a normal that's extending from the center. And when I say normal, surface normal, for the sake of it, we can draw it like this, and the length of that ray is gonna be 1. So it hits us like this. We're gonna extend it, actually, it's easier. And now this normal has a certain angle that closes with the light ray. So this is light, this is surface normal. So we have these two. Then depending on this angle over here, we're gonna take the color, the base color of the sphere, and then make it brighter or darker depending on it. The brightest possible point on this sphere is gonna be the point where the surface normal and the light are perpendicular to each other and go in opposite directions. And what I mean by that is that if we hit the sphere with this line over here like this, so you can imagine it going to the center straight, the normal is gonna go this way in the same direction. And that means that the surface is facing directly towards the light, which intuitively means that that part of the surface is the brightest. How do we calculate that? Well, we have dot product, right? I'm gonna do a video on dot product in the future for those of you who are not really familiar with vector stuff. But for now, just bear with me and yeah, we'll see. Dot product of these two vectors, if you take this one and this one, when you do dot product operation on them, you're gonna get a negative number because they're going in the opposite direction. When you do a dot product of these two, we're gonna get a first negative number. It's gonna be a number that's getting larger as we decrease the angle. So if we increase the angle between these two rays, dot product is gonna be smaller. What dot product does, it projects this one on this one. So dot product in general kind of represents how much a certain vector is going in the same direction as another vector. It's doing a projection from one vector to this other vector. So what happens here, a bit simplified, what happens is that this vector gets projected on this vector. So if we do this vector dot this vector, we're gonna get something, a number that's gonna be represented as you're going this direction this much, kind of, and what's gonna happen, you're gonna get a number. That number is gonna tell you that information. So let's say we have the same length vector. Dot product of this vector and this vector would be smaller than this vector and this vector over here, and dot product, when you come closer and closer, it's gonna get bigger and bigger and bigger. What that means in our scenario is that if you go further away or you change the angle so it's larger and it creates an angle between light and this ray that's super large, you're gonna get a number that's small, and that number that is small, we're gonna be using that number to create our color of the sphere. So I hope I managed to explain this in some way that makes sense. Let's try to do it in practice. We did the direction, right? So the light has a direction. The sphere has its own color, we're intersecting, all of this works. But the color is not the same on all points of the sphere. So what we're gonna be doing right now, we're gonna take this color, we're gonna affect this color in some way. So if I wrote 0.5 times this color, it's gonna get, pretty much it's gonna get darker because it's not 1. If we had 1, it would be 0.5, we get darker, fine, sure. If we multiply it by 2, it's also gonna change a bit. But the thing is, if you had, let's say if you had red set to 0.8, now it should be 1.6. It's not gonna make it more red. It cannot be more red than 100% red. So it's gonna clamp all the values that go above 1 to 1. So in theory, let's do this. Now it's white. Why? Because we multiplied it by 200, which means that whatever we multiplied it with right now, it's gonna be much larger than 1, and it's gonna clamp all of them to 1, and you're good to go. Let's remove this part. So we have this color. Right now, what do we need to do? We said that if we have a vector of the light and we do a dot product with the vector of the sphere, as I did over here. So if you do dot product of these two things, we're gonna get a number. Let's do that. Let's make a separate variable for that, and we're gonna call it coefficient, and we're gonna say that that coefficient is dot product of what direction? What is the direction? Direction is the direction of our light, so it's gonna be light dot direction, and we're gonna make this dot product with our surface normal. What is our surface normal? Well, question marks. We don't have it, kind of. We still don't have it over here. So, but we do calculate surface normal within this intersect function. We're just gonna add another out variable, because we want to get this thing out of this function. And then we're gonna do this. So it basically fills in this input variable. And that's cool. And not that button. And now here we need to create another, we need to create a variable we're gonna inject. So we're gonna do surface normal. Just gonna leave it like this, leave it hanging. Okay, so we have this coefficient. Yeah, and of course we need to pass it here. It compiles, nothing changed again, but our coefficient should be a number now, right? If we are on the part of the sphere that's pointing towards the direction of the light, our dot product is gonna be negative, right? So we're gonna see that in just a moment. So if we do this, it's already doing some crazy stuff. You can see that it shades a part of the sphere, but we said that our direction is pointing downwards. And the reason why I mentioned this negativity again is because this coefficient we get right here, it's actually negative. So we should be inverting this to get the right numbers. It should not be negative, because once you have the negative number, you multiply that negative number with your color and you get this kind of behavior. So if you do this, we get this inverted behavior. So it's quite interesting. Let's see what we can do, what more we can do. So the light is somewhere pointing down. Let's change the direction a bit just to see how that works. So if we move it a bit left, or not, we don't move the light, right? We move the direction, so it should be like this. That means that our x should be negative because we need to do this, right? Let's do that. Okay, so now the light is like this, so the rays are like that, and guess what? We're lightening the top right part of the sphere, and also we're light. You don't see like the front of the sphere is never really lit because the z coordinate is pointing nowhere really. It's just pointing straight. So, but we can move our z coordinate a bit. So we said if we go further in our screen, further down, we are negative. If we go closer, we're positive. So let's point towards the screen more, because we're not pointing anywhere right now. We're gonna point to -1, and then you get this direction from us to the sphere. And guess what? We can if we make it, if we set the direction to be purely z, we get the same thing we had in the last lesson. We get this straight flashlight thing happening again as the ball is jumping up and down. Nothing changes in its shading or illumination because it's perpendicular rays going towards it, and you get pretty much the same result. But I would like to do one more thing that's pretty cool, and I really like it before we go in further into more shading stuff in the next tutorial. I wanna build an interactive part of this, and for that we're gonna use mouse input as a start inside of this lesson. We might build on top of this later on. We might not. It's not really something that's crucial or important in this context. Let's say that we wanna, when we move our mouse around the place, so when you click and move your mouse, that we wanna change how these rays are pointing, and that's easy, and we're gonna do it like this. So just before our ray tracing, we wanna do some fiddling with our direction of our light, directional light. To be able to do that, we need to take the mouse input. So mouse input is in GLSL inside of shader toy is exposed over iMouse. So if I type iMouse X, I get a pixel or a coordinate inside of our pixel grid where my mouse is. So if I place my mouse here on the right, it's 800, and here it's 0, right? And usually how it works in graphics, this is 0 and this is 450 Y. It can be inverted depending on the system and depending how it's being set up, but it's usually like that. So you can do iMouse X, if that's a number that's between 0 and 800. We want to affect our direction somehow. So let's say we have light direction. Let's say that direction, we want to change X coordinate of it because we are moving our mouse on the X coordinate. We'll say the RX is iMouse X. So what do you think is going to happen when I do this? I said this goes from 0 to 800. That means that our direction.x is going to be 800. And 800 in this context where we go from minus 0.5 to 0.5, 800 is kind of a big number, and since it's super big, it's gonna look like it's coming from the side, and if we move our mouse left and right, it will not affect what we do much. Let's say we do, so if I do this or this or this, it changes direction. If we get to a number that's yeah, exactly. You see how much more it does than it should because it's a huge number. It's 800. Definitely not what we want to do. So you can get some granulation of it in the first X pixels. Like it's not a lot, but it's super drastic. It goes like, look at this. It's just crazy. What we need to do here, we have this eye resolution. .x. If you do this, then things change. Eye resolution.x, that's gonna be the resolution we see. So in this case, eye resolution x is gonna be 800. And now if I do this, we do see some movement, right? It does seem when we go right that it moves, when we go left that it doesn't move. And why is that so? Because we normalized our coordinate system between minus 0.5 and 0.5. Our light direction is moving between 0 and 1 all the time, which means that half of the coordinate system is never hit. We don't ever go to that other direction. And the thing we need to do to beat this, we gotta decrease it by 0.5. Now we normalized it in that sense. So if I do this, we see that you can see that I can even maybe zoom in, go full screen, why not, go crazy. So if I go right and left, you can see that it changes how illumination works, where the light points. But you also notice if I go left with my mouse, the light is hitting the right part of the sphere more. If I go right, it's hitting the left part of the sphere more. And there's a simple reason for it, because we're changing direction and we're using the x coordinate to get the direction of that light. So basically, if you have if you have a screen that looks like this, if you click over here, this is the direction. You clicked here, now we normalized only x, we're gonna normalize y as well. So right now it kind of looks like this more, but it's gonna look like that. And what happens, it changes direction like to this one, and this top right part of the sphere is gonna be lit. So if I press here, or yeah, now there is no y actually, so it's just shifting between left or right side of the sphere. So I hope that's okay, that you understand this part. Now let's do something different. We're gonna say light direction dot y is I mouse y. We now know that we need to do this as well, because we wanna have them between 0 and 1, and now we wanna normalize it between minus 0.5 and 0.5. If I do that, and my spelling is wrong, fixing that real quick. Okay, now we have y and x. I talked about the fact that if I click here, only top right part of the sphere is hit. If I click here, only top left part of the sphere hit. It feels a bit opposite, so I don't want it to work like that. I wanna have the feeling that I'm kind of moving this light source, although it's not moving. We're just changing direction. And the only thing we need to do here is actually this. And why is this? It's just because we're inverting the whole logic over here to make the direction look like position. So if I do this now, look at this. If I click here and move my mouse around here, you're gonna see that it kind of you can see how light changes. There's one thing that I just noticed, that to all of you watching this right now, it might look like nothing is happening actually, because we should probably put the z thing back to 0, and we want to point downwards, because now it's gonna be far more obvious what's happening in terms of directions. So let's zoom in on this one. It's still too dark, so we might want to instead of having z that's complete 0, we should go with 0.1. So we extract it a bit more towards our eyes. It's still not as strong as I hoped for. Still not good enough. Nothing is happening. Let's see what's wrong. Actually, I don't see anything, right? Oh yeah, exactly. I did a mistake, and I was thinking about direction or position instead of direction. So direction is actually going the opposite way. So if you do it like this, we get something. But let's do this. So now if you take a look, you're gonna notice that we do have changing directions. Okay, one more thing. I noticed that the color is not something is definitely off with the color, and let's try to figure out what's wrong with it. So we did normalize this, and this points downwards, and this points a bit. We could possibly do this. Then we can basically beam that light towards the sphere, that it looks much better. But yeah, we don't get that much of the difference now. I was talking about normalizing these kinds of things at the beginning, and whatever I change here, I put this normalize here, and I'm good. And I did the same mistake again, but I didn't do it here. I actually did it over here. And you might have noticed that I'm changing X, I'm changing Y. I don't normalize anything. And that's gonna cause a lot of calculation problems later on. So when we change this X and Y, we need to do this instantly. We need to normalize it. We change the coordinates completely. It's definitely not a normalized vector with magnitude 1 now, with God knows what, depending on what you put. So we need to say direction equals normalize light direction. Light. And now we get a better looking sphere because it's finally normalized. Our calculations are not worked, and I really like doing comparisons. So let's bring this one over here, and then let's bring this one over here. If we take a look at what we did, this is what we had for the first one, and this is the second one, the one we got today. That's it. We're done for today. Thanks again for following through. If you liked this video, don't forget to press like. If you want to see what's going to be happening next, please do subscribe. It's much appreciated. And until the next time, where we're going to be tackling fog shading, you can see on this demonstration, our sphere is going to look much more realistic than it looks like now. So until then, stay safe and goodbye.